We're going to work on determining the rate laws and calculating the value of the rate constant. In this experiment, they've given us information of the initial rate for the reaction, and they're asking us to determine the rate law and to calculate the value of the rate constant with correct units. So the rate law takes this form: rate equals the rate constant times the concentration of the reactant raised to the power of m times the concentration of the second reactant raised to the power of n. And what they're asking is for us to solve for m, n, and to calculate the value of that rate constant with the correct units. When you are solving for these powers, you're actually comparing rate to concentration. And when you do that, you're able to solve for the power of that concentration. So if I'm solving for m, I've got to find two experiments where the concentration of I2 stays constant or doesn't change. So if I'm solving for m, I'm going to look for two experiments where I2 does not change. So that would be experiment 1 and experiment 3. Now it doesn't matter which order if I divide these numbers up in, but I try to make the math easier, so I try to aim for having the larger number on top. So solving for m means I would have to take experiment 3 rate, divide that by experiment 1, and this should equal to the concentration of H2 raised to some power m. So this is going to give me 3 equals 3 to the power of m, so m equals 1. Now I want to solve for n, and I'm going to do the same thing. I'm going to compare the rate to the concentration, but I'm going to pick the two experiments where H2 remains constant. So to solve for n, I'm going to have to use the information from experiment 1 and experiment 2. So the rate would be 4.23 divided by 0.952, and this equals to 3.25 divided by 0.732 to the power of n. This is going to give me 4 equals 4 to the power of n, so n equals 1. Now that I solved for my m and my n, I can go ahead and give a proper rate equation. So rate equals K times the concentration of H2 raised to the power of 1 times I2 raised to the power of 1. Now it's asking for us to solve for K. So I have the rate law. I can use any of these experiments to plug in my numbers and solve for K. So I'm going to go ahead and pick any experiment. Let's just pick the first one. And I'm going to substitute my numbers in. Okay, I'm going to solve my for K. So K equals 0.735. Except I need some units here, so I need to go back and think about my units. Now, the rate is always going to equal to molar per time, and in this example, molar per second. My K units I'm not sure of. My concentration is molar times my concentration, which is molar. I'm going to get all of my units on one side, so this is like saying divided by molar, divided by molar. All of the units that can cancel cancels out, so the units for K is 1 over ms. So that means my proper units is going to be 1 over molar and 1 over seconds. So I've solved for my rate law, and I've solved for the value of K with correct units. Let's take a look at another example. In this example, they've given us information of the initial rate for the reaction, and they're asking us to determine the rate law and the value of the rate constant. So I'm going to start off with my generic rate law, which is rate equals K times the concentration of N2 raised to some power M times the concentration of H2 raised to the power of N. In order for me to solve for M, I've got to find two experiments where the concentration of H2 doesn't change. So I'm looking at experiment 1 and experiment 3. So let's solve for M. And we're going to compare that to concentration. All right, this is going to give me 2.07 equals 1.439 raised to the power of M. Okay, this one is a little bit harder to see, so I'm going to have to do a little bit more math, and I'm going to convert both sides to logs. So I'm going to take the log of 2.07, and I'm going to take the log of 1.439 to the power of M. Now, by doing that, I can get that power M outside. So it becomes log of 2.07 equals M times the log of 1.439. I can go ahead and divide the log of 2.07 divided by the log of 1.439, and I'm going to get M equals 2. Okay, let's solve for N. So if I'm solving for N, I've got to find two experiments where the concentration of N2 remains constant. So that's going to be experiment 1 and experiment 2. So let's start with that. I'm going to go ahead and do 4.65 times 10 to the 4th over 2 times 10 to the 5th. And I'm looking at the concentration of H2, so that would be 0.553 over 2.38, all raised to the power of N. All right, 4.65 times 10 to the 4th divided by 2 times 10 to the 5th is 0.233. And 0.553 divided by 2.38 is 0.232 raised to the power of N. This one is easier to see, so N equals 1. Now that I have my coefficients, I can go ahead and write down the rate law. Rate equals K times the concentration of N2 raised to the power of 2 times H2 raised to the power of 1. The next thing I want to do is solve for my K. So I'm going to go ahead and plug in some numbers, and it really doesn't matter which experiment I go with. So I'm going to go with experiment 1 here. Don't forget to use the proper power. So concentration of N2 to the power of 2 times the concentration of H2 to the power of 1. So I'm going to go ahead and solve for K, and K should equal to 1.74 times 10 to the 5th. But I do have to worry about my units, so let me do some work on the side here for the units. I know that power, or the units are going to be molar per second equals K times molar squared times molar. So when I divide my numbers here, I'm going to get K equals 1 over molar square times second. So the units here are going to be 1 over molar square and 1 over time. So I've got my K and I've got my rate law. Good luck and keep practicing.